All right, so let's talk about bound objects. Just work, please, pen. There we go. Bound objects. Okay, just realized I wasn't recording any of that, so let me just say it again. So just in a quick review here, the force of gravity decreases as we move farther and farther away from our planet. And in order to get up and off the planet, you need to supply some energy. So this can be in the form of kinetic or chemical energy, and say like a rocket. And we've worked on, how fast you have to be going to shoot your rocket or your satellite off into space and have it never come back. So now what I want to talk about is something that is bound to Earth, which means it's in Earth's gravitational well still. It's not at infinite distance. So the moon might be something like this, or any satellite that's up around the Earth, but that is in now a stable orbit. So in order to get something to do this, we need to give it enough energy such that it's up above the Earth. Okay, so we have to compensate for the gravitational potential energy. We need to put it up there, but then it also has to have EK, right? Because it's in a stable orbit. So we think about it when it's like that in these terms, right? We say the centripetal force to keep the object orbiting is provided by the force of gravity. In reality, the mechanics of getting it up there are we need to use a rocket ship or something to push it up to this height, and then to also push it at a lateral angle to that value so that it ends up in an orbit. All right, so let's talk about this. We'll start here. We'll say that, the centripetal force is provided by gravity. And we've dealt with problems like this before, and we would say it's like this. mv squared over r is equal to g mass of Earth, mass of the object, over r squared, okay, in that orbit. Okay, so let's do a little bit of algebra with this thing. If we multiply both sides by r, we get this. Okay, so now, if we want to get this in terms of energy, we can multiply each side by 1/2. Okay, so now look what we've done. We've said that 1/2 mv squared is equal to 1/2 gmem over r. All right, so let's just keep that in mind for a second. And then let's just think again about this satellite. All right, so we know the satellite has two things going for it, right? It's got EG and it's got EK, right? So we could say then that the total energy of the satellite would be then EG plus EK. All right? Or let's just write that in a slightly different way here. Let's just write it like this. The total energy of that satellite, right, equal to EK plus EG. Yeah, and remember that the absolute value at this orbital height, right, the absolute value at this orbital height is negative gmm over r. Okay, negative gmm over r. So then we get this. We get that 1/2 mv squared plus negative gmm at that orbital height should be equal to the total energy of that satellite up in orbit. Now what we've just done, this other part, is we've made 1/2 mv squared equal to 1/2 gmem over r. So we then get this. 1/2 gmem over r, okay, and that's at that orbital height, of course, plus negative gmem over r naught. Well, that's interesting. 1/2 subtract a whole will give me what? Okay, so we would say then this is the absolute value for a bound object. The absolute energy for a bound object. And on its own, it's sort of useless. Okay, on its own, it's sort of useless. But what we're going to use it for is we're going to say, what is now the binding energy? So what binding energy essentially is how much energy must we add to free this object from the gravity well that it's in. That's what binding energy is, and it's actually just a really simple step to do so. So just to reiterate exactly what I'm talking about here, saying this maps the gravitational potential energy, right? This maps the gravitational potential energy as objects move up and down inside a gravity well, okay? But a bound object, right? What here you can think of it kind of like this way. I can add gravitational potential energy, right? And that's going to move the object, up, say, from the surface farther out. But if I just consider that, then at this height, it's going to have a velocity equal to 0, and it will tend to fall back towards the planet. Does that make sense? So once it's in a stable orbit, once it's up somewhere above the planet going around and around, okay, it has more than just gravitational potential. It's got those both together, right? So we figured out that the E total is equal to 1/2 G MEM over the R naught of the orbit. So the binding energy then is just to say, okay, we have these two types of energy. How much more do we need to add in order to pull this object away from the planet? Okay, so it's the energy to overcome, if you want, the binding to the planet. It's just called binding energy. So all you have to do then to figure that out is if you know that the total energy of this object, we say it's a bound object, this object's bound, and its total absolute energy is equal to negative 1/2 G mass of Earth, mass of the object over R naught. We just need to know how much more energy we have to apply to it to get up to 0. So what we do is we say we need to find the delta E to pull this object out and never have it come back. So in order to do that, the delta E, of course, is just final minus initial. So 0 minus negative 1/2 GMEM over R naught. And that just turns it into a positive value. It's the same thing, but it's positive, right? So binding E of any satellite, in other words, how much extra energy I would need to give it to pull it off the planet, to pull it out of the well, is just the positive 1/2 G MEM over R naught. So here's an example. Calculate the binding energy of the moon. Okay, so there's our info, and now we just need to set it up and solve for the binding energy of the moon. So we've got 1/2 G, 6.67 times 10 to the negative 11. That's kilograms, kilograms negative meters squared newtons. Mass of the Earth, 5.98 times 10 to the 24 kgs. Mass of the moon, 7.34 times 10 to the 22 kgs, like massive numbers. And then the orbital radius of the moon, 3.8 times 10 to the 8 meters. And solve. Like 8s. Okay, so that doesn't look like an 8, but that's an 8. So the binding energy of the moon should be 3.86 roughly times 10 to the 28 joules. So if you want to send the moon away and have it never come back, you need to give it this much extra energy than it already has. And that's it for this.